All right, so today we were going to be doing a review of the homework. It's snowed out, and so the homework's going to be due on Thursday. So I'm going to be talking about vector field display, and then the vector field homework will be not done, but it'll be done in class. I'll still give you the kind of tutorial section so you can read through and know how to load things in and display things in peer view and so forth. All right, so first we'll see a couple of interesting visualizations. So this is looking at what happens to blood when you send it through your pump, right? And so this is looking at a simulation of flow through an impeller, and they're going to look at what happens to blood flow. And this particular presentation was made for a conference, and so they wanted to show how you could use a system on a screen with a little force feedback device, in a kind of desktop VR, or inside a projected multi-wall cave environment. So this is showing streamlines going through. We'll see streamlines in a minute. It's showing damage locations where the poor blood cells get chopped up as they go through. And then here, this is showing how a little packet of space gets rotated and squished in different axes as it goes through the impeller, right? As it gets squished too much, it's actually going to damage the red blood cells potentially. So this is showing a trace of where there was potential damage to a cell because its deformation was too high as it went through the impeller. So that gives you kind of blood spattering of where the blood would be spattering, I guess. You can also look at streamlines of how flow happens through the impeller at a particular time step. All right, so here they've done a slice through to show you the regions as well.
Here we have our full transitional flow volume. The bottom plane is showing 3D velocity fluctuations, which are indicative of turbulence. And the plane on the left is showing streamlines velocity, so we can see the bounds of the boundary layer. So now we are enabling slow and fast velocity streaks. At the inlet of the volume, which is to the left, we see that these are orderly, elongated streaks. And when they reach the turbulent region, they become more pale. So now we've added more isosurfaces showing 3D velocity fluctuations, and those are another indicator of turbulence. So here we're looking at a turbulent spot. We're slightly downstream. The volume erupts into full turbulence. And now we're zooming out. And we are going to turn off our streamlines velocity fluctuation isosurfaces. And we're going to enable our feature detection condition. So now we see some isosurfaces. And what we're interested in is finding these near the inlet. And these are predictors of turbulence spots, which will eventually lead to full turbulence. And so here we've located one. And so now we're going to constrain the volume.
So here they combine two of my favorite things, right? The rainbow color map and uniform transparency into the same display. In this case, the uniform transparency is on a plane, so you're pretty sure about what its shape is. And so it does actually give you an indication by being a watermark of showing which things are above and which things are below. If it was a surface, you'd have a hard time understanding both that surface and what it was slicing through.
To the area immediately around this feature detection condition, so that we could study it in more detail.
Well, that's very user-friendly.
Now something they're doing here that's helpful is they're projecting on the side and they're projecting on the floor, right? And so this is something that if you wanted to see multiple views but you only have one image, and I talked about this with the shadowing, right? And so you can do a similar thing where you can take a slice on the edge or you can take a slice through the middle and move it out to the side, and then you can kind of have the 3D geometry and then the slice things out to the side to provide context.
Now we're going to add some planes on the left and right side. Again, showing streamwise velocity. We're going to deactivate that plane out the far left. And so this is the volume that we are going to study as it evolves through time. And so we're going to go ahead and re-add our streamwise velocity streaks. And again, you can see these are elongated and orderly at the inlet, and further downstream, they become chaotic.
So here what they've done is they've computed streamwise vorticity as as a scalar field, and they've drawn isosurfaces of that scalar field. So within that is high vorticity and outside is low vorticity. So they've kind of computed the regions of the thing that they want to see, and then just show you the regions as surfaces. All right.
In this paper, we present methods for visualizing complex network structures in biological tissue. Shown here is an opacity map created from stained mouse brain tissue using high-throughput microscopy. These new techniques allow large volumes of data representing tissue at the microscopic level to be collected at rates exceeding 100 megabytes per second. The dark spheres are cell bodies of neurons and glial cells. The unstained filaments make up a dense network of microvasculature, supplying nutrients to the surrounding tissue. The first step in our algorithm is to use vector tracking methods to quickly trace the structure of the volumetric network. This provides us with a skeleton representing the medial axis of the tubes in the network, as well as connectivity and radius information. After the network has been segmented, standard methods can be used to visualize and query the created graph. Here the network is rendered using imposters colored based on the diameter of capillaries. Individual capillaries can also be picked and expanded to explore the surrounding network. We then associate volumetric information from the original data set with the graph structure. This allows us to selectively visualize the network using volume visualization or isosurfacing algorithms. The same picking and searching functions can be applied in the volumetric visualization.
All right, so here what they've done is they want to display the data with volume rendering in a way that's clear, but there's so many blood vessels that they include each other. So the question is, how do we get just the ones that we want? And rather than picking a region, they've run basically this complicated analysis algorithm to find the centers of all the vessels, and then they pick in that vessel tree, these are the ones I want. But they don't just render the kind of center lines in the vessel tree, they actually do volume rendering, and they use this vessel tree as a mask, right? So they kind of expand their vessel tree by the size of a blood vessel, and then do volume rendering everywhere, but it's putting zeros in the volumes where there's nothing to render. And so it's kind of again, the main problem in 3D rendering, as you're finding out, is how do you show what you want to show without including things you also wanted to show and see them more clearly. This is their idea now.
By applying queries to the network graph, we can begin to relate the microvascular network to surrounding tissue. Here we show a volume rendering of microvessels cradling a single cell. Note that our volumetric encoding only stores data local to the network. Since the cold regions often contain noise, this provides a cleaner volumetric visualization and allows a more liberal selection of isosurface values without having to worry about noise in the resulting surface. Finally, one of the major features of interest to biologists studying microvasculature is the association of cells to the nearest capillary. We use fast sweeping to create a Voronoi diagram from the vascular surface in linear time. Cells that lie in the capillary's Voronoi region are then associated with that microvessel. They can then be rendered with it as simplified spheres or using the cell's actual volumetric data.
All right, so basically what they're doing here is saying, I want to see all the cells that are closer to this blood vessel than any other blood vessel and see what the surrounding environment is, right? Or vice versa. All right, so homework grading. Remember to put your PNG files into the zip in addition to your state file. And remember to put the final design image, the 4.png, into that as well. It just saves me hunting it together and putting them all together. Homework schedule. So homework 2 deadlines, it moves to Thursday. Homework 3 we're going to do in class on Tuesday as our design exercise after we do the kind of review of the current homework, and I'm working on homework 4. So we're going to, at the end of the semester, have only 4 homeworks that we're going to be doing for final projects, which is okay because the last one was going to be a contest instead of somebody's in the class, and they'll get more attention to the people's in the class, and I'm happy with that. All right. So today we're looking at the question of how do you display flow. We've looked at 2D scalar fields, things that are just values in space, and 3D scalar fields, and now it's vector fields, both in 2D and in 3D. There's kind of 2 different ways you can look at vector fields. One is a steady state vector field, where it's kind of, it's the same over all time, or a snapshot of an unsteady field is kind of the same over time. And the second is an unsteady state. So if you look at a river running, at any particular moment, the vector field is not the same as it was the previous one. There's a number of application areas, and everything from airflow to electromagnetics to fluid flow. So some example vector field kind of features we're looking at here is a flow with 2 different centers that are rotating kind of opposite to each other, right? And so you can't tell from this picture whether the flows are kind of going this way and it's going to the right, or they're going that way and it's going to the left, but one or the other. So this is a vector visualization that we're going to talk about called line integral convolution. Basically, this could be flowing this way, this flowing this way, and all the flow in between is going there. Here's one where they're rotating in the same direction as each other. So the flow kind of comes around and then in and then back out and around and in, and there's a saddle point in the middle of this where kind of flow comes to a halt and then comes back out around. So here's 2 centers of rotation and a saddle point, are some of the features that we'll be looking for in vector field visualization. This is 2 sinks, and so a sink is where fluid is leaving the environment. If this was the bottom of a kitchen sink, this is the drain where it's going out. Here, this sink has 2 drains. It goes down here, it goes down here. So flow can come to the middle. It kind of comes to a stop at the saddle and then randomly picks which valley to fall off onto into one of the sinks. This is a source where there's fluid entering the world, and a sink where there's fluid exiting the world. So there's no saddle in between. Fluid basically comes in, goes out, comes in, goes this long way around. It comes out, goes back, goes out. Okay, so this is basically what electrostatic fields look like with a positive and negative charge. A magnetic field with the positive north and the south pole will look kind of like this. All right, so some of the questions that we ask about these vector field visualizations are these. Where are critical points in the flow? Right, and so these are sources and sinks. Centers of rotation. Vortices. So a vortex is in kind of a center of rotation in 3D that's along a line. It's the center of spin. And then where there's kind of fastest, slowest, stationary. Right, so where there's interesting stuff happening in the flow field, where there's particular things. Then there's also what's the shape of the field, right? And so where's laminar versus turbulent? Let me explain this. Right, so laminar flow is a flow that every nearby point is very close in velocity matching to its neighbors. And so if you have basically air moving slowly over a wing, on top surface you'll have a laminar flow as it goes up around. If it goes fast enough, there'll start to be mixture and there'll be turbulence. So that small changes in initial position produce large changes in trajectories throughout. And so the definition of turbulence is interesting. Over the years there have been several of them. It's called like vortices. How do you decide what this is? It's like you know when you see it. When everything's mixed up together, it's turbulent. When it's all flowing in levels, it's laminar in layers. All right, and so where is their rotation? All right, so another kind of question is transport. And so this is like pollution, right? And so if you want to know, okay, if we release toxic chemicals here, where are they going to go so we can warn the people to get out of the way? Or conversely, I've just found some toxic chemicals, I want to run the flow backwards to find out who to blame for putting them here, right? And so you can kind of flow things forwards and backwards. And so this is the kind of inverse is where, so transport goes two ways, right?
That could also be diffusion, right?
Yep, indeed.
Like air fuel.
Yep. So this has got both diffusion
I don't know if that's the right term, but or mixing.
and flow, right? All right, and then there's another one, which is really a tensor field question, is where stress causes strain. And this one is kind of not like the others. So what you're going to realize here is the fact that we've got so many very different kinds of questions for vector fields. This lecture is going to look a little bit more like a grab bag of techniques, each of which applies to a particular thing, than the scalar fields, where it was kind of a corpus of work where we understood how to cover the space. But we're going to have examples that work well and don't work well for each of these. And then another question that we ask for each of these is, does it work in 3D or does it only work in 2D? We're going to see some examples of places that it works. So again, we're going to go through a bunch of different techniques. Particles moving through the flow, traces that they leave. Glyphs, so we're going to see more glyphs than we saw in the scalar fields, but still not as many as we're going to see in the multivariate, which will come Thursday. How to do textures to understand how the flow works, and then flowing surfaces through the space. And then finally color, which you'll remember from the pane lecture. All right, so particles are basically smoke puffs, and so in real wind tunnels they would release little puffs of smoke that would flow along and you could watch them move through the space. In simulations, they're basically massless particles, so they don't interact with the flow, they don't have inertia, they just kind of go along exactly with the vector field. And this is usually displayed through animation. If you have a particle system with one frame, it's a bunch of points in space. It doesn't tell you anything about which way things are flowing. There's two ways to think about advection, or the motion of these particles. One is basically in a single time step, which is a steady state flow. So if you drop them into a river flow simulation, and so okay, at this time step, how is the river flowing? You would keep the vector field the same, and the particles would flow through that. So it's like they were moving in time, but they aren't. They're moving in kind of space along a trajectory. Or you can run the river flow simulation forward, and the same particles will now follow a different trace through this field because their vector field that they're in is different at every time step, right? And so you might be interested in either one of those questions. From a kind of a computational point of view, you don't really care. You just switch out the field that you're following. But from the domain science point of view, the question that answers is very different.
But the vector field itself is changing dt, right?
Right, but you can freeze it in time, and you could ask the question, at this moment in time, what's the vector field like? At a later moment in time, what's the vector field like? And then you can animate particles, not through time exactly, but as if there was a steady state flow at that field. There's another question about what release pattern do you put the particles in. You can put them on the side of the sphere and see how they go. A flat spray, which gives you some more structure to the pattern, kind of a uniform line or a grid. And then there's a question about, do you release them all at once and then they flow, or continuous release of particles, or bursts of particles. And we'll see different examples of that as we go. All right, so here is an example. I guess I deleted example one. And so this is looking at flow inside a mixture chamber. So these are two mixers that are spinning the same way to try to mix up fluids. Now here they're using the rainbow color map as kind of a nominal coloring, right? It kind of says, where did it start, right? The red one started here, the blue one started there, and the question is, do they mix up together so that the different colors are near each other? So it works pretty well. Again, I would choose a banded one for that, but so this is basically showing the particles in a line at one time point, and then where they ended up after integrating. And you can see that it is actually doing a pretty reasonable job of putting the material all over the place that started there. All right, so this is looking at calculation of supernova atmosphere for different geometries. And so this is a simulation of photons that are emitted from a companion star to a white dwarf that went supernova. And this watches as the photons traverse the gas, and they leave the kind of region around the supernova, right? So the trajectories show you kind of how they bounce around in the gas, and then the spots that accumulate on the edge show you a histogram of where the different photons with different energies left the area.
Okay.
All right, so this is looking at two electromagnetic beams colliding in a collider, and they're charged, and so as they come together, they kind of focus each other and then blow apart as they pass. And so you can watch kind of as they come into clusters, interact, and then come apart. This is basically two galaxies coming together to understand over maybe millions of years. And so that with timescales of galactic things, kind of how they interact. All right, so the benefits of using particle systems is that they show advection directly, so you can kind of watch where something's going to go. Cluster motion shows kind of critical points and features of the flow, right? So if everything collapses into a point, you're saying, okay, that's a sink. If things kind of come together, stop, and move again, you can start to see critical points. And then motion directly shows where particles end up, right? So for the problem of transport, where do particles end up, this is exactly what you want, right? So put them at the source, watch where they go, and they show up. This was done in the cuvette, right, to see where things ended up. If you want to remember where the particles come from, it's actually going to be really hard to mentally reconstruct what the trajectories were, so you need a trick. Let's run it backwards in time. Okay, particles ended up here. Where did they come from? It'll show kind of distribution of things where they came from. And so this is, again, an idea of what space do I want to show in. There's also what time scale do I want to show in the visualization in. And then, all right, so occlusion and confusion. So if you saw all those particles, you weren't seeing kind of each individual one in the galaxy formations or the particle collisions, and it can be hard to know where they come from. And there's a question about how do you place them and time the release so that you see what you want to see.
Now these experiments, the particles are actually the thing you're looking at, right? Versus in airflow, the little massless things are just sort of tracing the flow of the gas, right?
Well, in the wet flow, the particles were actually just locations in the fluid.
Right, but the other ones, like
the particles were the interesting things.
Yeah.
That's right.
So they weren't because you sort of described them as sort of a synthetic thing that you put in to visualize it versus the thing that, in the galaxy, it's actually the thing you're visualizing, right?
That's right.
Yeah,
That's right.
so it could be either one. Yeah.
All right, so if you want to kind of remember where a particle came from, or in a picture show a time series, you can leave trails behind these particles. And so this is similar to the streaks in wind tunnel experiments where they would kind of continuous flow. So you can use geometry, different lines or illuminated lines, tubes or ribbons. You can, again, either doing a single time, it's called a streamline, or over time, it's called a streak line. So if you let the river simulation run while the particles move, it's called a streak line. If you do it first, it's called a streamline jargon. All right, and there's the same question about how do you release them, kind of shows how they fill up space. So it turns out that placing and spacing of this matters, right? So this was the 1996 Clerk and Banks paper. This is uniformly seated streamlines, right? So the points that these started on were a uniform grid, and there's all kind of interesting patterns, not to do really with the data, but with the uniform grid sampling. This is, they ran optimization to make the lines mostly uniform in density, and they would both grow and shrink them so that they would kind of get to the right length, and they would add and delete them to kind of give a uniform sampling. And it gives a better uniform distribution of where these critical points are in the flow than if you just do this uniformly. This is not yet in pair view, but there is at least a random seed placement that you can do in pair view, which is better than the uniform because it doesn't alias to the underlying grid. All right, so here's an example of doing streamlines around flow around the space shuttle, both with kind of uniform color and with color according to perhaps pressure. So we're seeing this vortices show up around the edges of the wings as there's round, circular flow going there. Here's illuminated translucent streamline. So the idea here is we're looking at, I think it's a benzene ring, and we're looking at the electric field around the molecule. And so these are basically like little tufts of hair that kind of show you, that go along the gradient direction of the electric field. and this is a zoom in on the field around one of these particles. And this is a picture from an actual print, and so the quality is not as good as we would get in the original visualization. So here's why illuminated and transparent matters. This is if you take streamlines and you just draw the lines themselves and they're all the same color. And it's a big mess. You can't tell what it is. If you illuminate this, if you make the streamlines transparent so you can see through to the other ones, now you can start to see a little bit through that there's something going on, but you can't understand the 3D shape of the streamlines. So if you illuminate them as if you had kind of hair, then basically what you can see is the ones that are coming out front and the ones that are going through behind, and you get a much better idea of what the shape is, as well as being able to see through to ones that are behind.
Is there a method for illuminating in pair view? Or illuminating in streamlines?
This has not been, yes, this is the case where this will be useful for you thinking about your final design, and if you're kind of thinking about how do I want to program something, or what do I want to do in my Google Summer of Code to add to pair view, yeah, this would be a good one to do. All right, so this is about halfway between streamlines and particles, right? So this is leaving streaks behind the particles, and so this is looking at three different flow at 3 different levels. A higher up flow is blue, a lower down flow is white, and the deepest flow is black. And so they've used basically color and luminance variation to separate the fields. And so we're seeing you can attend to one of these flows at a time. I don't think you can attend to all 3 of them at the same time. You can kind of see that the black is quite different than the white in some locations. And even if we stop the flow, you get an idea of locally in time how the flow is behaving. All right. So a tube is basically if you took a particle and you traced it, that gives you a line. If you extend and make a little surface around that line, you get a tube. And so one way to do hair-like transparency illuminated in pair view is you put tubes on the objects. And then the tubes themselves are illuminated. If you zoom out enough, they start to look like lines, and so you can also do then transparency. In fact, one of the in the homework you'll see an example of how to do line integral convolution is to do that trick, do multiple transparent ones. So these again they're lit, and so you can see them more like the hair, and you can also show auxiliary information, either the color on these to show the value, which you could also do with lines, but also you can vary the radius to show another value. Right? So you can have a couple more data sets mapped onto the vector field that show you a couple of scalar fields along with the vector field. So here's an example of flow coming in, swirling around, and then leaving. And so we're using both change in radius and change in color to indicate what's going on in the flow. And there's a couple of other glyphs that we'll talk about in the middle there later. All right, so this is an example of the electric current in the thorax. Here the color shows polarity, positive versus negative charge. And then these go along the gradient lines to show you how the flow is going through the thorax as the heart is pumping. This is the magnetic field and the electric field, which hopefully you'll see in the image everywhere are perpendicular to each other. Turns out to be true. So this is a tokamak. This is one of the 2 ways to produce fusion. This is the way where you constrain a particle beam to kind of lie in a plane and they fly around and slam into each other and produce fusion. And so this is trying to show what the fields look like that are trying to confine this moving charged particles to understand what's going on with the flow. And so here we've got basically one color for tube for magnetic field, one color for electric field. So this is a volume rendering of thin threaded structures within multi-valued scientific data sets. So here the velocity is yellow and green, the vorticity is purple and pink, and there's halos. So what does that mean? So halos means that around the tube that's in front, you've got a region that masks the tubes behind. So there's kind of a dark region around. And that gives you an understanding which is in front and which is behind. Whereas if you just mix the colors and don't have opacity around, you can't as easily tell this. And so the reason that we can see kind of where this blue is with respect to the purple is we've got this black halo around it that's showing you that that's kind of the one that's in front. All right. you can, instead of just doing a tube, if you want to see changes in orientation, you can stick a ribbon and have it traverse along the particle trajectory, and then this can actually reveal kind of streamline vorticity, which is vorticity along the direction of the stream as well. Here's another example of ribbons from the simulation of a severe thunderstorm, showing particles coming in, being pulled up, and then spinning around in the vortex at the center of this thunderstorm. Here's examples of ribbons together with transparent isosurfaces on a delta wing and in a rotary aircraft. So this is a helicopter. You can see the blades spinning around and then the flow that happens induced by the blades around. All right, and so one interesting thing you can do is release the tubes in a structure. And so here we're saying we have an even spacing of these tubes, and in laminar flow regions, basically they stay together and they stay kind of close to each other. Where there's separation of flow or turbulence, this shows where there's kind of this uniform thing splits into two parts, and this shows where it starts to have a vortex, right? And so you can see the twisting induced and the separation induced from the uniform initial location. All right, so here they're trying to use transparency, which is a little hard to use, and then they put things in motion, and there's actually features in the transparent objects that start to see, because there's differential speed of motion on the different layers, you get some idea of the depth, right? And so this is kind of like the screen door transparency applied to looking at flow fields. And then they try every crazy texture pattern they can throw on it to see which one's the best.
What is that?
Say again?
What is that?
Yeah, that's a good question. I don't know what this is. I should look it up. But it's getting bigger and smaller.
It's empty in the middle, though. It's kind of
It's
weird.
empty in the middle. Slow around
Skin
something
effect or
around.
something.
Okay. So the streamline characteristics, the benefits are they show the advection directly. The cluster motion shows critical points and features right as they come together, flow apart, and spin. It shows where flow comes from and where it goes. The streams by themselves don't tell you which one is which, right? Unless you're going to put some aeroglyphs or color or some animation, you're not going to know which way is forward and which way is back. And they can show twist and advection as well. So there's lots of occlusion if you have lots of lines, and so you have to deal with halos, and even then you can't see very far into the space. Don't know which direction is forward and back, and there's the same question about how do we space them in a way that doesn't show alias artifacts and also does capture the thing that we want to do. If you have them too dense, you can't see what you want to see. If you have them too sparse, you might miss what you want to see, right? And so one approach to that is to allow the scientists to interactively place the streamlines, and then they can explore different areas without any particular point in time being a problem. Or in an animation, you can show different streamline starting locations to kind of scan more of the space.
So for like the aerodynamic stuff analytically, is this better, worse, different than the old style wind tunnel with the smoke and all this kind of stuff?
This is exactly kind of a graphics implementation of the old style wind tunnel.
So the question is it, if I'm a aeronautical engineer or whatever, which one is going to be more efficacious for me? Which, in other words, is this better or worse than the old school smoke in the tunnel kind of thing?
So it's better in that you didn't have to actually build the thing to put in the tunnel.
Right.
It's probably better in the sense that if you've got a tube instead of a smoky surface, you're going to see the shape of it much more clearly than if you had the smoke, right? If they could have pulled tubes through the actual ones, that might have been a perceptually improved thing.
Yeah.
Yeah, so I think it's better and better.
So it's easier to interpret, yeah, correctly.
Yeah.
Okay.
And then you can also, unless you got really clever with your chemistry and pressure, you'd have a hard time coloring the puffs according to what the local temperature and pressure characteristics were, but you can do that in the visualization. All right, so we've looked at particles, we've looked at streamlines, we're going to look now at glyphs. So these are little individual icons that are scattered in the field, and you change the behavior, the kind of visual characteristics of the icon to show information. Look at arrows, hedgehogs, tufts, and the tensor glyph, which is going to be the most complicated glyph I think we'll see. All right, so this is the real old-fashioned way they did it, right? They would take these little flexible pieces of rope and they would tie it onto the missile. They would put the missile in the wind tunnel and they would watch how these things flapped, and whether if they flapped a lot, there was turbulence. If they stayed straight, there was laminar flow. Which way they pointed showed you which way the flow was going. So this is, again, a uniform spacing of arrows. They're the same length, and they just show direction, and they're colored, I can't think, according to velocity,
Rainbow.
magnitude here.
Rainbow.
And yes, our favorite, I don't know, there's a lot of purple in that rainbow.
There's blue,
Yep,
green.
it is the rainbow, yep. Shows up
Shimmer.
everywhere.
There's no sad face.
9 out of 10. Oh, there's no sad face, thank you.
So with this presentation, you probably just put happy faces on the few of them that don't have the rainbow color.
Thank you. Excellent. Now your notes will be wrong, but the slides are right. Yes. So you get a chocolate bar.
Yeah?
I didn't tell people that if you point out in my slides where I missed to put a unhappy face, you get a chocolate bar.
Dark chocolate, please.
Dark
Yeah.
chocolate, of course. Is there any other kind?
Some people think there is.
And so the reason that I have only one missing one is that last class, there were lots of people that got chocolate bars. All right, only 3. All right, so then there's the same question about where do you want to release these. Here it's uniform release, and it kind of shows how the direction changes along the rake. This is not my favorite, most dense visualization of flow.
It's also rainbow.
No, well, okay. All right. So the interesting question is, these are tough. So this isn't say just a straight vector. Let's make this thing curve along the flow. Interesting question is, which way do these things flow, right? So you might think, well, they flow towards the darker end. Well, sometimes. You might think, oh, they flow towards the pointy end. Well, sometimes. And so which way are these things flowing?
They flow away from the diffuse end.
Sometimes. So they flow away from the background color.
Yeah.
Right? And so it's weird. You would think, you know, that something about the shape would be the more compelling thing, but it's really kind of which way is away from the background. They could be arrows or they could be comets, and it depends on which way is away from the background. All right, so these are kind of straight line glyphs. They're just local oriented things. These are longer when the magnitude is greater, but they don't have an arrowhead to show you direction. And these are curved line glyphs. And so these are basically uniform in length. And so again, these are kind of uniform spacing, random spacing, and then optimized spacing. Right? And so the optimization here basically makes them uniform in density, and it captures the kind of different fields better. And so what they've done basically is blurred the images and made the blurred images kind of uniform in brightness. And that's how they move these things around until they are better. And try to make it as even as possible.
But don't you lose the distortions? Like if you make it evenly spaced in the last case, the second picture gives some, that there are some distortions.
The second picture gives it there's some distortion. So what are you seeing here?
By making it streamlined, like in the third
Yep.
density, you're losing a piece of information.
So here you're losing a piece of information, but that information is aliased with the grid, so it's not useful information. Here it's randomly sampled, so there shouldn't be information. So you may be seeing things here and here that you don't see here, but the point is the things that you're seeing aren't in the data. They're in the sampling you use to get the data.
So
Here, not as much, but it's not as uniform. So you're missing places just because you didn't happen to put a line there. Here it's maybe more uniform, but then you get these kind of artificial, interesting artifacts that are because of the way the sampling interacts with the flow.
Well,
All right, the flow probe. This is the most complicated glyph that we're going to encounter. So this is to show you everything that there is about flow in a local place and space. So the first thing you have is this blue ring around the bottom. That's a reference for everything else. Its job is to show you how other things move. Then you have this green ring that flows this way and flaps this way. Let's start with the curve itself. You've got a blue arrow coming out. This is showing you which way the flow is going. It's got yellow stripes that shows you whether there's rotation in the direction of flow, right? There's a yellow bulb at the bottom. If it's big, there's lots of acceleration. It's speeding up as it's going forward. If it's small, there's deceleration. It's going backwards. The green flip-flop thing is showing you whether the flow is diverging as it goes forward or converging as it goes forward, and it's compared to the blue reference ring. And then the red ring shows you if there's shear, right? So if it's flowing faster on this side and slower on that side, you get shear as it goes forward, right? And so this is showing you everything that you can understand about what's going on in the local flow field. And it's really cool. It's only got one negative, maybe two. What's the negative?
Good luck putting more than one of them.
Good luck putting more than one, yeah. This is awesome if you're holding around trying to kind of measure the flow at one point, or sparsely putting, but if you wanted to put very dense with this, you'd have a hard time understanding. Exactly. All right.
What was the second?
What's the what?
Maybe two things wrong.
You have to do a lot of thinking.
Okay. Let's make it
Right?
that was.
And so if you have to, if you wanted to learn only one or two things, maybe this was telling you more than you wanted to know. Yep. All right, so here is this kind of a simplified version of that glyph used in a flow around the blunt fin, along with some streamlines and an idea of kind of what's happening around each of those. And so this is about as dense as you want to put these and still see what's going on in the circles. Tufte would also tell us that we don't want such a strong grid that it dominates the entire visual scene. But
Are they giving some sort of a different nominal color to the shear line? Because it's like red over there and orange, or is that just to say what face of it you're seeing?
I think it's just shading. I think it's just darker.
Oh, it's
over
like in
here.
shadow over there?
And it's brighter over here.
Okay.
Yeah. So this one's kind of more facing away from the light. But here you can see the benefit of the blue ring, right? It's like, okay, which is the kind of main axis of this with everything else curving? It gives you a reference frame to judge the rest of
So
the
that the
display.
blue is normal to the direction of flow, is that it?
Yep.
Okay.
Yep. All right, so it turns out that the place you put the arrows also matters. If you give people an image like this without this line drawn, and you ask them to draw a line, they'll connect these things, right? So if they're close enough to each other in position and orientation, you actually will perceive a line going through there. It turns out that there's other neurons in your visual system that kind of extend lines out, and when they meet other extended lines, they form these apparent contours, even when there's no contour in the image. And it's useful to us to be able to see such things. So this is taking a uniform grid of arrows versus a head-to-tail arrow flow. And so here you can follow the flow much more easily than understand that this one goes over to this one in the flow. And so if you can do the head-to-tail arrows, it can be improved. And there is actually a trick in peer review to do this, and I had in homework what that trick is. It's basically you do the streamlines first, you subset the streamlines, and then you put the glyphs on the streamlines, and you can take the lines away if you want, but you'll have head-to-tail flow on the arrows that you're showing. All right, so this is Turk and Bank's next iteration, where they put the arrows head-to-tail and made them uniformly spaced, and made them curved, and made them larger or smaller to show the speed of the flow, right? And so this is, takes a long time to optimize, but it really does a good job of densely, in 2D, showing flow around the whole region, right? So if you want to know, okay, where's my balloon end up here? You follow the arrows, they're nicely arranged for you head to tail. We're a little confused here. I guess we're not because it's going this way. And it's going to go right there in this instantaneous flow, right? All right, this is another glyph approach that they try to do glyphs in 3D. Of course, there's
We
music.
present an interactive real-time visualization tool which uses novel techniques to show vector data. We are looking at the time evolution of a point source earthquake simulation which shows volumetric velocity. Here the velocity magnitude is shown by the color and size of the ellipsoids, while the orientation is encoded as white and black spots on the poles of the earth. Now let's examine how this method works to see why it is better than previous method. Traditional tools use colors, glyph shapes, and size to show scalar information. However, it is necessary to show orientation for vector data. Our method uses procedural dipole texturing to indicate orientation of a glyph shape. We paint a white spot on the head and black spot on the tail of the glyph, which enables an unambiguous and view-independent representation of vector information. We can show the displacements of the glyphs based on the underlying data to reinforce interpretation. Furthermore, we can also show a 3D lattice. This lattice helps us to see the depth better by providing a context to the glyph. We can interactively modify the lattice resolution as desired. Now let's use this tool to explore a magnitude 7.7 earthquake simulation on the southern San Andreas Fault. We build a rich context by adding a geographic map, then adding another map which shows the fault slip rate on the southern San Andreas Fault and an isosurface for the ground stiffness. We can tune this isosurface to show the Los Angeles basins clearly at the desired stiffness level. We are looking at the impact of the big one in this region. The regions with white spots are moving towards the camera, while the darker regions are moving away. This gives us an intuitive notion of ground motion. By refining various parameters like color, shape, and size, we are able to see different features of the seismic wave, like regions undergoing intense shaking, and
Here,
source directivity,
they've disappeared the
which
ones that
channels the
understand,
waves towards
which
Los
is
Angeles.
very helpful in this technique.
We
right?
can
Because
also
otherwise you
investigate
could
the
see
wave
most of the
amplification
surface.
and lingering shaking in this region, which is thought to be caused by entrapment of energy in the shallow sedimentary basins. By changing the glyph geometry to a comet-like shape, we are able to see a flow-like nature of seismic waves. Notice the vortices in some regions. These features have not been seen by previous methods and are intriguing to the scientists.
You could
So
put a
again,
smiley
this-
on the,
Say again?
you could put a smiley on the, it uses rainbow.
Yeah, you
Yep.
could put a smiley on this, and you get some chocolate too, don't you? I'm gonna run out, this is good.
I don't buy this one. I think with the animation, you don't need the silly white-black business, because you can see the direction the particle is moving.
Uh-huh.
I think when you stop it, it's useful.
So when you stop it, it's useful, and when they use transparency to remove the ones that have low magnitude, then you
Yeah,
start
but
to see things
their
inside.
thesis that this funny coloring or tadpole shape or whatever is, sperm shape or whatever is somehow helpful, I don't think.
Yeah.
So what was the color came in like partway through, so is that like the S wave?
He never explained it.
Okay,
I'll have to call him up and ask him.
you're not really gonna do that.
Huh?
You're not really gonna do that.
He was a contest co-chair with me for a
Oh,
number of
really?
years, so yeah, I'll be glad to
Call him on his,
call him up. What
Call
the
him.
heck was the color? And why the rainbow? He'll know. If he sees me coming, he's like, he actually showed me, he came to me in conference, like, oh, okay, I know we use a rainbow, but that wasn't my, yeah. Because of David Borland, I somehow have a reputation as the anti-rainbow color map guy. That's what it's like. All right, so here's some more rainbow. So this is flow radar glyphs. All right, so this is saying I want to see how flow happens over an entire time series of a video. I don't want to have to watch the video and try to remember for every location at every time what was going on. And so this is basically the beginning of time is at the center, and then the end of time is at the end, right? And so this shows, the color shows the speed, And you're saying, okay, it starts out this one flowing to the right, and then ends up flowing around this way, and then ends up flowing to the right again. Right? This one flows to the right, then back to the left, then back over, and then back. So this gives you kind of an orientation time histogram of which way the flow is going. Gives you an idea if it's consistent between regions, if it's consistent in a particular region, and so forth. They also had the approach of trying to show the uncertainty. Right, so here the line shows you the average, and the kind of arc shows you the standard deviation in their estimate of that. So one way to get this is you can start particles at slightly different locations and see how much they diverge. Another is you can track error in your algorithm and kind of directly show this. Now, when I saw this, what I thought they were going to say in the talk was this is a way to do a spatial summary, right? So in other words, if you try to zoom out on this, you have a problem. You've only got a few glyphs covering the whole space, and if they're point samples, you don't really get a good understanding of the variation. But if this was a summary of all of the different ones within that region, now it shows you the spread of these as well as, so that says, okay, if you want to zoom in, here's the place to zoom in because I'm not doing a very good job of showing you the variety inside here. So this uncertainty could either be because of spatial variation or because of, kind of numerical variation or uncertainty. All right, so glyphs. You can show complicated structure at each glyph location. They're hard to use in 3D, right? So we saw the glyph C, when they were completely dense, you saw the outside of the cube, and that was all you could see. And so you can basically modulate their presence based on some scalar field, right? They only show up when the things I care to look at are present. The size, right? You have a trade-off. If you kind of make them big enough to see their complex shape, then you can't put them very densely. And then the question is, what's the best placement of that? Interactive probing is one very good way of kind of moving a glyph around, especially for the flow probe, to see what's going on in the scene. All right, textures. So basically the idea here is to say, okay, let's make a texture that by its very construction shows the flow that's going on in the field. And we're going to see several different techniques to do this. The first is linear convolution, and my animation almost works here. Right. We're going to talk about what linear convolution is in a second, so actually I'll do it now. So basically linear convolution is you take a noise pattern. I used to could say like when your TV is not tuned to a station, but that doesn't happen anymore, it turns blue now. And so basically it's a salt and pepper, mix random black and white surfaces, and then you blur along the direction of flow. Right? So what happens is along the direction of flow, things become the uniform texture, but as you happen to pass through brighter and darker regions across the flow, you get kind of an idea of which way it's going. This is then animating that kernel, so over time it goes from the front to the back, and you get a pattern showing you which direction the flow is going, which you don't have if there's not an animation. Very effective in 2D. All right. So this is oriented lick. Or spot noise, and so basically here you've got little tufts that you're scattering down, that each one locally shows what the flow direction is, and the lengths give you some idea of the speed. And then you don't completely fill in the space, so you can still see the individual elements, and it gives you the idea the flow is going to the right on this one and to the left on this one, again because these things always flow away from the background color perceptually. Actually, let me, okay. So this is three-dimensional lick with and without halos. Right, so that texturing worked really well in 2D. In 3D, the question is how do you see through to the inside? Right, and so the idea here is, in addition to modulating the color, you make the opacity vary so that the bright things are opaque and the dark things are transparent so you can see through. Then you can use the same halo trick to say, okay, around the white things is a dark halo so you can see which is in front of the other. At this point, we're almost basically drawing streamlines that are white streamlines with halos, and this is another way of drawing that, right? And so You can call this a texture, you can call this a streamline at high density, I don't really care which one you call it. They both have the same impact in terms of being able to see through areas where there's very low values into higher areas. And again, this is modulating, at least down the center, how much the texture is present by how much flow characteristics there is.
Is our viewpoint moving in that picture, or are we seeing the flow?
The viewpoint's
flowing?
moving.
Okay, so it's not actually, the thing is static and we're spinning around this way and that way.
Yep.
Okay. All right.
All right, so this is basically adding on halos plus colors. So on the left, colors from red to yellow with increasing temperature, and on the right, it's more saturated with streamwise vorticity. And so you can again add to the texture some other scalar field information. This is color is showing the magnitude of vorticity, and this is very interesting because it shows this really interesting kind of shock wave pattern, repeated shock wave going down through the flow that you wouldn't have seen necessarily without this additional color channel. It's a very strong pattern in the flow. All right, another approach is to do line integral convolution, but only seed it at locations where there's interesting things happening, so that you can basically kind of have the flow pattern where you care about it and see around where you don't. And then this is a 2D version of spot noise. Spot noise is where you basically take those little line segments and you splat them down, and you make dark ones and light ones and dark ones and light ones, and you randomly do that. It turns out that in the limit, spot noise with infinite flats and line integral convolution turn out to produce the same image. And so you can decide how you wanted to render it, which was ever faster on your rendering system. So this is the same thing on a slice. One slice is the surface of the Earth, and another slice is kind of vertically, so you can get an idea of what happens as you go way up in the atmosphere and what's happening kind of on the surface at the same time. Of course, a subset of the data. All right, reaction diffusion is how it's pretty clear our fingerprints appear. Zebras get their stripes, leopards get their spots. So these are two or more chemicals that diffuse across space and then react when they get into proximity with each other, and these form these stable patterns over time. And so the idea here is you drive this reaction and diffusion with the flow, and that tends to stretch these features along the direction of flow. So these are little kind of cockroach things that all run upstream on the flow, right, to give you an idea of what's going on. And so here is looking at different critical points. Electric field from a dipole, electrostatic charge, a saddle, and a sink. So the other thing that they did was increase the diffusion in areas where there was uncertainty in the flow, right? And so then these things start to become fatter where there's uncertainty and narrower and more precise where there's certainty. So this is a good attempt at showing not just the flow, but how sure we are about the flow, which is very seldom done in visualization, but very often useful to think about, right? Are these numbers precise? If they're not, how do we indicate that imprecision in the display? Fred Brooks talks about this as not having more verisimilitude than veracity, right? So it doesn't look more real than is warranted given the data that you use to generate the picture. So this is a comparison between using the reaction diffusion textures, using kind of just oriented ellipsoids, and using line integral convolution to give an idea of these the same shape. So you get the most dense display here, but you don't know the direction. Here you know the direction and some density, and here you kind of have neither of those benefits. Another thing that you can do is actually squirt dye into the fluid and watch how it either diffuses or also goes under flow. And so this is showing a yellow source and a blue source in the Gulf of Mexico over time to show how the sea currents flow. One thing that I talked before about the release pattern. So here they've released in a rake along the edge, and they release blue, stop, yellow, stop, blue, stop, yellow, stop. So this gives you a spatial pattern and a temporal pattern that shows you how mixture happens over time and gives you kind of a better idea of what's going on than if you just continuously flow the thing with the same color.
And they turn to green when they mix.
And they turn to green when they mix. So this is using both reaction diffusion and, both transport and anisotropic diffusion. So it diffuses more where there's less flow, and so you can start to see things mix more when there's...
Someone else can get a chocolate bar.
Oh, it's a rainbow again? All right.
Who else wants a chocolate?
Alex gets another chocolate
Oh,
bar.
I'm just trying to give it away to someone.
I know, you're so
I
nice.
can give one to my wife then.
Or you think you get 2 chocolate bars in one day? Yeah. Oh, rainbow doesn't show up on the white. Oh, okay. Sorry, I need to not take all my time doing this, but this really will help. So I'll reprint these notes so that there's actually the right smiley faces on these guys. Text color black.
You really hate the rainbow color pattern.
I do. And you are starting to convince me that I don't like continuously varying color maps, but I always would like to have discrete banded color maps. All the way there yet, but
I actually did an experiment with that.
pretty close.
Excel has these, you can do a surface map thing, if you give it a matrix. I just did like a waveform, 3D waveform.
Uh-huh.
And yeah, you can adjust the, how many different gradations it uses, and around 8 to 10 is about right, and it doesn't really matter what color you use. It'll do about the right thing. If you try to make it continuous, it becomes unintelligible.
All right, so this is looking at linear convolution kind of built from the ground up. So this is if you just take a noise pattern and you advect the noise pattern, right? So this is a little bit like a particle system where the noise happens to put particles in different places. This is where you average as you're doing this, and so you start to see what looks like linear convolution over time. Longer streaks where there's faster motion, shorter streaks where there's slower motion.
So they started with Gaussian white noise, and then they applied the vector field to it, and then they're blurring as it goes around.
Yep. And so this is adding dye into the flow, right? So this was kind of surprising to me
What?
that kind of the green is moving faster. It's completely correct, of course. The thing on the outside moves faster because in one revolution they all come back around. And so it's useful to me to have that to get an idea. So here are the 3 different colors, show you the 3 different starts, and you see that they stay at the same radius, and so it's just completely circular flow. So this is constant flow that changes its orientation. It's particularly relevant this time of the year. Why is that? You advect dye. It's going to make the Olympic rings.
I was thinking of yellow snow.
All right, so you need a couple more. But then you get the Olympic rings. All right. We're going to skip this. We saw one very similar to it recently. All right. So this is kind of the texture, flow, turbulence in the real world. This is off the Chilean coast, mountains spinning vortices in the clouds as the flow goes by. Take a uniform noise texture, you advect it, you see what you...
But this is actually a photograph.
This is actually a photograph.
Yeah.
Yep. All right. So texture, at least in 2D, it shows the entire field, right? There's some local features in the texture kind of everywhere. You can animate the entire field, and you can't therefore miss critical points, right? So it's very good at showing you where all the critical points are. In 3D, we're in big trouble, right? Because you have a hard time seeing through the outside to the inside. There's some tricks you can use to try to help with that. It also can be hard to get quantitative information out of texture. All right, so stream surfaces. So instead of kind of bringing in from a point and producing a line, you can bring in from a line and produce a curved surface. Right? And this directly shows you how the thing behaves. So this is streaming inside the back of a television set from back when we had CRTs. So it shows you the temperature and kind of how a kind of uniform slug of air flows in and then out the side vent, and some of it goes out the top vent.
Oh.
These are stream surfaces past a cylinder and showing the different kind of vorticity that happens behind.
Very patriotic.
So here's a transparent stream surface that's kind of shed from a ring that comes into the beginning here, or shed from a line, and it splits on both sides of the cylinder, and then we start to see some kind of turbulence in the flow as it goes around behind the cylinder. So this is not quite a surface, right? This is kind of individual points that start out in a regular grid pattern, and then you can see how they separate as they go across time. Again, it's a green and then a red and then a green and then a red, and you can see how those behave over time. All right, so this is, again, good for initial concentration. This is where the stuff started. Where does it end up? It only shows a subset of the field, and if you get significant divergence, these things just form giant surfaces that cover the entire viewpoint. And again, occlusion can be a problem. All right, so color, right? You can use it as an auxiliary data set to show magnitude. We've seen that several times here. Age, release location, pressure, so forth. It can also be used, and we talked about this in an earlier display, to show the vector flow field direction. And I don't recommend using it to show the vector flow field direction because all the other techniques that we've seen are an improvement on that. However, some techniques are ambiguous, right? So linear convolution is ambiguous which way is forwards and which way is backwards. So here, they use the color wheel to kind of pick a direction, right? And so now, at each location, you've only got two choices. It can be going this way or this way. The color wheel can tell you which of those that it is. So you can at least tell, is this flow direction and this, and another one is the same orientation, the same or opposite directions because they're opposite colors or the same colors. And so this helps disambiguate pretty clearly which regions are which.
But the luma is causing all kinds of weird distortions in the, like right there, that line that goes down from there.
It looks very much like,
kind of like there's a
divot.
Yeah.
Yep. You change the brightness and you change the apparent height.
That's bizarre.
I'm not convinced that that isn't actually on. Yeah, so the magnitude is actually used for relief shading. So this is shaded according to magnitude. So that what you're seeing there is there's low magnitude in that dimple.
So but that line that extends out to the down
here?
to the right, no,
Yep.
down from your point.
Yep.
That looks like a valley.
Yes,
Yeah.
right, and that's because of the color map
Yeah.
changing. That's
Yeah.
right. So they were having interference between the brightness change in the color map and the brightness change in the shading, and that's unavoidable. All right.
Oh.
Another approach is to say, okay, what we're going to do is we're going to reduce our vector field into a scalar field by coming up with a pattern that is my vortexness, right? And I'm going to take this vortexness pattern, I'm going to scatter it throughout the entire data set and find where there's high vorticity, and then I'm going to isosurface or color according, or other 3D scalar technique to show that particular quantity. So here's kind of a saddleness detector, a vortex-like detector, and so in the video we saw at the beginning of today, there were those surfaces, there were basically surfaces of isocontours of this vorticity, so you could extract regions that you're interested in by not having you figuring out was the field doing what you expected inside there, but rather image analysis figuring out what was happening in there. So this is 2D with not the world's best color map. Here's 3D, right? So there's different kind of 3 different surfaces: a red surface, a yellow surface, and a green surface. And it's trying to say, okay, which regions within this box have high vorticity, high other features that I'm looking for. All right, so color benefits. There's the kind of the chimera that says you can show data over the whole field, but it's not so good to see what that data is at any location in the field. It can be good for nominal labeling, release location or age, And it's good to overlay a scalar field, magnitude or pressure on the data set, not what you want to use for the main display. All right, so we're going to look here at some combination techniques. So this is looking at a field around 2 condenser plates. And so we basically see a slice through this that's line integral convolution on that slice. Then we've got streamlines with glyphs on them showing you just an unambiguous direction of these lines and their symmetry. And then we've got a color map in the plane showing the magnitude of the field, which unfortunately is the same color used for the red and green, but not red and greenness, right? So this is magnitude here, it's north and south, it's kind of a positive negative charge there.
No.
So this gives you a good high density on a slice, but then you can see how that changes as you come around because of the low density streamlines and the arrow glyphs help with
What
display.
is same color to the top region?
Yeah, so green and red here means positive and negative charge. Green and red here means magnitude.
And ironically, they didn't need to label the positive and negative because you could infer that
Yep.
from the direction of the field
So-
lines, but, you know.
Almost perfect. Yeah, all right. This actually works awesome if you're in the head-mounted display like he is. When you're looking at it from the side, it looks fairly cluttered and hard to see what's going on, right? So head track stereo really helps you pull things apart in one of these displays. So whenever you're doing a complicated 3D velocity field or scalar fields, you want to think about how do we at least do stereo. And in pair view, you can do stereo if you have the hardware on the machine that you're doing that. All right, so this is line integral convolution and a velocity mask. Right, so this basically says I'm only showing the texture pattern where there is high velocity. Everywhere else it fades away. So it helps focus my attention on what I need to see. And then I can see around to see context behind the texture. This is the same thing, and what we're seeing behind is the landmass, kind of mountains versus plains and the ocean, so we can see what's going on as well as seeing the texture flow over top of it. All right, so this is, they've done some topological analysis on the flow field, and they draw glyphs at each of the critical points. Spinning glyphs for centers of rotation, different glyphs for saddles and sinks, and then connectors that show the critical paths in between these critical points that gives you the topology of the flow field. And then, this is the flow behind the cylinder. And then they have a vertical slice showing line integral convolution and a horizontal slice showing line integral convolution, so you can see the whole field in those particular planes. All right, so what I've done, and I did it for several years and then stopped because it looked the same every year, thank goodness. This is kind of my best guess at how each of these things worked well in answering these questions, right? So this is kind of your chart for things to start with if you're trying to do visualization with these techniques.
You know, for a visualization guy, that is absolutely hideous.
Yeah, well, thank you very much. This one.
Wow.
Yeah.
It's like, what
Yep.
the hell is he on about?
Yep.
Yeah.
Yep. It was me writing at the end of class furiously on the board and then writing it in here. So there's also credits for better work that is done from the different examples that I used. And that's it for the vector field visualization.